Space is vast and full of mysteries. The cosmos stretches out in all directions, filled with countless stars, planets, and phenomena that continue to baffle and intrigue scientists and astronomers alike. Among the myriad of celestial wonders, black holes stand out as some of the most enigmatic and fascinating objects in the universe. Among these mysteries are black holes, objects so dense that not even light can escape their grasp. These cosmic giants are formed when massive stars collapse under their own gravity, creating a point in space with an incredibly strong gravitational pull. The boundary around a black hole, known as the event horizon, marks the point of no return. Once anything crosses this threshold, it is inevitably drawn into the black hole, never to escape. Astronomers recently made a remarkable discovery: a lone black hole drifting through our Milky Way galaxy. This wandering black hole, unbound to any star or system, moves silently through the vast expanse of space. Its solitary journey offers a rare glimpse into the behavior and characteristics of black holes that are not part of binary systems or galactic centers. This is the first time a lone stellar mass black hole has been observed in our galaxy. Stellar mass black holes are typically found in binary systems, where they interact with a companion star. However, this discovery of a solitary black hole provides a unique opportunity to study these objects in isolation, free from the influences of nearby stars or other celestial bodies. The discovery has sent ripples of excitement through the scientific community. Researchers and astronomers around the world are eager to learn more about this lone black hole and what it can reveal about the nature of these mysterious objects. The data collected from this discovery could help answer fundamental questions about the formation, evolution, and behavior of black holes. It offers a unique opportunity to study these enigmatic objects in isolation. By observing a black hole that is not influenced by a companion star or other nearby objects, scientists can gain a clearer understanding of its properties, such as its mass, spin, and the effects of its gravitational pull on the surrounding space. The discovery was made possible by a phenomenon called gravitational lensing. This effect occurs when a massive object, such as a black hole, warps the fabric of space-time around it. As light from distant stars passes near the black hole, it is bent and magnified, creating a lensing effect that can be observed from Earth. This effect, predicted by Einstein's theory of general relativity, occurs when massive objects warp the fabric of space-time. The warping of space-time causes the paths of light rays to bend, much like how a glass lens bends light to focus an image. This bending of light allows astronomers to detect objects that would otherwise be invisible, such as black holes. This warping can bend the path of light, acting like a giant magnifying glass. By studying the way light is bent and magnified by the black hole, astronomers can infer its presence and gather valuable information about its properties. This technique has proven to be an invaluable tool in the search for and study of black holes. The discovery of this lone black hole provides a tantalizing glimpse into the hidden population of these objects in our galaxy. It suggests that there may be many more solitary black holes drifting through the Milky Way, waiting to be discovered. These hidden black holes could hold the key to understanding the true number and distribution of black holes in our galaxy. It also opens up exciting new avenues for understanding the life cycle of stars and the evolution of galaxies. By studying solitary black holes, scientists can learn more about the end stages of stellar evolution and the processes that lead to the formation of black holes. This knowledge can help us piece together the complex puzzle of how galaxies, including our own Milky Way, evolve over time. Black holes are among the most fascinating and extreme objects in the universe. These enigmatic entities have captured the imagination of scientists and the public alike due to their mysterious nature and the extreme conditions they represent. They form when massive stars collapse at the end of their lives. This process is one of the most violent and energetic events in the cosmos, often resulting in a spectacular supernova explosion that can outshine entire galaxies for a brief period. Imagine a star, much larger than our Sun, running out of fuel. Over millions of years, this star has been fusing hydrogen into helium in its core, producing the energy that makes it shine. But eventually, the fuel runs out. Without the outward pressure from nuclear fusion, gravity takes over. The balance that has kept the star stable for so long is disrupted, and the core begins to collapse under its own immense gravitational pull. The star's core collapses in on itself, crushing the matter into an infinitely small point called a singularity. This singularity is a place where the laws of physics as we know them cease to function, and densities become infinite. This singularity is surrounded by an event horizon, the point of no return. The event horizon marks the boundary beyond which nothing can escape the black hole's gravitational grip, not even light. Anything that crosses the event horizon, even light, is trapped forever by the black hole's immense gravity. This is why black holes appear black. They do not emit any light that we can see. Black holes are often found in binary systems, where they orbit a companion star. These systems are fascinating to study because the interaction between the black hole and its companion can reveal much about the nature of black holes. These binary systems provide clues to the presence of a black hole, as matter from the companion star spirals into the black hole, emitting X-rays. The intense gravitational forces at play heat the infalling matter to extreme temperatures, causing it to emit X-rays that we can detect with space telescopes. However, the recently discovered black hole is different. Unlike the typical black holes found in binary systems, this one is solitary. It's alone, drifting through space without a companion star. This solitary existence makes it a unique object of study, as it allows scientists to observe the black hole's properties without the complicating influence of a nearby star. This makes its discovery even more remarkable and provides a unique opportunity to study these objects in isolation. By studying this isolated black hole, scientists hope to gain new insights into the nature of black holes, their formation, and their evolution over time. This discovery opens up new avenues for research and deepens our understanding of the universe's most extreme phenomena. Imagine a bowling ball placed on a trampoline. The trampoline represents the fabric of space-time, and the bowling ball represents a massive object like a planet or a star. The ball creates a dip in the trampoline's surface, illustrating how massive objects cause a curvature in space-time. This curvature is what we perceive as gravity. Now, roll a marble across the trampoline. The marble represents a beam of light or a smaller object moving through space. As the marble passes near the bowling ball, its path will curve due to the dip. This is similar to how light bends when it passes near a massive object in space. This is a simple analogy for how gravitational lensing works. Gravitational lensing occurs when the gravitational field of a massive object, like a galaxy or black hole, bends the light from a more distant object. Massive objects like black holes warp the fabric of space-time, much like the bowling ball distorts the trampoline. This warping affects the path of light traveling through space. Light, traveling through space-time, follows these curves. The greater the mass of the object, the more pronounced the curvature and the more the light bends. When light from a distant star passes by a black hole, its path is bent. This bending can create a variety of visual effects, such as arcs, rings, or even multiple images of the same star. This bending can cause the star to appear brighter or even as multiple images. The phenomenon is known as gravitational lensing, and it can magnify and distort the light from distant stars and galaxies. By carefully studying these lensing effects, astronomers can infer the presence of a black hole, even if they cannot see it directly. They analyze the patterns and distortions in the light to understand the properties of the massive object causing the lensing. The recent discovery of the lone black hole was made possible by observing the way it magnified and distorted the light from a distant star. This discovery has provided valuable insights into the nature of black holes and their impact on the universe. Gravitational lensing is not just a fascinating phenomenon, it is also a powerful tool for astronomers. It allows them to study objects that are otherwise too faint or too distant to observe directly. For example, galaxy clusters can act as gravitational lenses, magnifying the light from even more distant galaxies behind them. This helps astronomers to see further into the universe and to study the early stages of galaxy formation. The concept of gravitational lensing was first predicted by Albert Einstein in his theory of general relativity. Einstein's equations showed that massive objects could bend light, and this prediction has been confirmed by numerous observations. The Hubble Space Telescope has captured some of the most stunning images of gravitational lensing, revealing the intricate and beautiful patterns created by the warping of space-time. Future space telescopes, such as the James Webb Space Telescope, are expected to provide even more detailed observations of gravitational lensing, helping us to unlock more secrets of the universe. As our understanding of gravitational lensing grows, so too does our ability to explore the cosmos. This phenomenon not only confirms the predictions of general relativity, but also opens new windows into the mysteries of the universe. Gravitational lensing reminds us of the interconnectedness of the cosmos, where the presence of massive objects can influence the path of light across vast distances, revealing the hidden structures of the universe. So, the next time you look up at the night sky, remember that the light you see has traveled through the curved fabric of spacetime, shaped by the invisible hands of gravity. The discovery of the lone black hole was a testament to the power of the Hubble Space Telescope. Hubble, orbiting high above Earth's atmosphere, has been providing stunning images and groundbreaking discoveries for over 3 decades. In this case, Hubble was observing a distant star in our Milky Way galaxy. Over time, astronomers noticed something peculiar. The star's light seemed to brighten and dim for a brief period. This subtle change in brightness was a telltale sign of gravitational lensing. By carefully analyzing the light curve, astronomers concluded that a black hole was passing between Earth and the distant star. Hubble's sharp vision and precise measurements were crucial in detecting this faint signal and confirming the presence of the black hole. The lone black hole is estimated to be located about 5,000 light-years away from Earth. To put that into perspective, 1 light-year is the distance that light travels in a year, which is about 6 trillion miles. This means the light we see from the black hole today started its journey towards us 5,000 years ago. The black hole is located in the direction of the constellation Sagittarius, near the center of our galaxy. This region of the Milky Way is densely packed with stars and other celestial objects. Finding a lone black hole in this crowded environment is like finding a needle in a haystack. However, the unique signature of gravitational lensing allowed astronomers to pinpoint